Okay, thank you, Kay, for the introduction, and a good afternoon for me, everybody, because here it's about 5 p.m. Matter of fact, as you said, I am quite a regular attendees of this session because always, we see cutting edge research. And I want to give you an update of the research we are doing in the framework of this research project funded by the European Community, in which we are using UHPC in structure exposed to extremely aggressive environments. And as a matter of fact, as you will see at the end of my presentation, now we have these structures designed, built, and fully under real working scenarios. So the problem was we need to identify the tensile constitutive behavior to design them. And we followed two different approaches. One was obviously back analysis of flexural tests. For the other one, we needed a test which was quick to be performed, also for quality control purposes. So we validated, I call it indirect tension test, and I will show it a little bit later. As a matter of fact, this is a work which has been done in collaboration, first of all, with my colleague Francesco Lomonte from my university, but also from the colleagues of University of Polytechnic de Valencia, Pedro Serna and his group, who actually organized 1 month ago the BEFIB conference in hybrid mode, but was also nice to see several of us there in person after such times. Well, just a quick overview of the project. The project is now going towards its conclusion because we will end in March 2022. We have been working for 4 years, 14 partners, 50 universities, 2 research centers, and several industrial partners. And as said, we have built structural demonstrators. So which was the objective? Obviously, the formulation and validation of material compositions to be used in extremely aggressive exposure. We have structures in marine environment and structure exposed to chemical attacks, and we characterize the mechanical performance, the durability as well, to incorporate these properties into a durability-based design approach, which we actually employed in 6 full-scale pilots. Actually, we do have 2 pilots in Italy. In Tuscany, they are structures servicing geothermal power plants. We have 2 offshore pilots, one for mussel farming and another is a scaled offshore wind floater. We have a precast pontoon element in Ireland, and we retrofitted a structure in Malta with the same materials. And actually, we are now working on numerical models which combine mechanical and transport properties to be able to go to, friendly, I would say, or practitioners-oriented durability design-based methodologies. So this is just a nutshell of our idea. When you go for design, you have a minimum required performance, and then you will design so that you will have a minimum safety factor. But actually, the degradation mechanism over time lead to the decay of the structural performance, so you need to intervene with repair, and this repair can become more and more frequent over time as long as deterioration proceeds. So actually, if you go with UHPC, not only you have better mechanical performance from 0, but you also have lower degradation, so your first repair will be delayed in time, and this compensates the unavoidable higher cost that you may have in the beginning. And in our approach, we had also self-filling, which can further delay and can also lead to improve to the cover thickness, for example, for optimizing the structural dimensions. So we worked with different mixed designs in the beginning, try to optimize them for our purposes. You can see here the completions that we used, SEM1 and SEM3. We wanted to use both. This is according to the European classification. SEM3 is now actually what we are more and more frequently going on because of the sustainability issues. It contains quite a lot of slag already in the mix. We add slag as well as supplementary cementitious materials, and we use a different type of fibers, steel fibers, short, straight steel fibers, or also amorphous alloy fibers. The difference in the quantities that you see is just because we kept the same fiber volume fraction, which is 1.5%. And for the self-healing, the last row that you see, the crystalline mixture, is the self-healing stimulator. So this is a quite usual conventional mixed design, this kind of material. The quantity of fibers was optimized for the structural purposes that we had in mind. Actually, these mixes here were used in the Italian pilot, so they are basins in geothermal power plants. We started obviously with a lab work, experimental characterization. We casted slabs from which we obtained a different kind of specimens, and we also casted beams for the European standard test on FRC. And the experimental plan also included this, we called it Double Edge Wedge Splitting test, DEWS, the mechanism you can see in the left of the slide. And we validated it as able to yield straightforward tensile constitutive relationship, quote unquote, of the material. And obviously we wanted to compare with the results that you can have from an inverse analysis of the flexural test that you perform on this. So we performed a classical inverse analysis, hypothesizing a constitutive relationship, stress strain and stress crack opening after the peak. Obviously, when you go then to convert the crack opening part into a strain, you need the structural characteristic length, which depends on the model that you employ. If you use a plane section approach, could be the depth of the cross section. We use also fine italics, and then you have to calibrate it with the element size. But this is classical procedure that we employed. So we wanted to identify from bending test the constitutive relationship through inverse analysis. But then, since we said that our double edge wedge splitting test is able to yield directly the stress strain relationship and the stress crack opening relationship, we want to make this comparison. So these are some of the results that we obtained for our materials. On the top you have the experiments, and on the bottom you have in black curve the experiments, and in orange and blue the models, the numerical predictions that we had based on finite animal simulation or a classical plane set approach. So as you can see, we had a flexural strength, maximum strength ranging between 17 and 20 megapascal, depending particular mix that we use it. And these are the lows that we identified from back analysis. You can see that in one case, for the reference, refer to the red curve because that is the average of the different tests we performed. We have a slightly strain softening behavior after the cracking, whereas we have a moderate strain hardening for the other mixes. Anyway, the tensile strength was about 8 megapascal, and the strain capacity ranged between 0.2, 0.3% and 0.5% at the maximum. Anyway, we deemed it satisfactory for the applications that we had in mind that I will show in a while. The important thing for us, refer to the graph in the bottom, was that the tensile stress strain and then stress crack opening relationship that we identified from our back analysis, as compared to the curves that obtained from the double edge wedge splitting test, you can see is perfectly in the range of the experimental results. So this means that what we identify from our DEVS test surely can be employed for the design of our materials. So these are some of the conclusions of the work related to this part that I presented. Our main purpose was that our indirect tensile test procedure was effective in identifying the stress strain and stress cracking constitutive relationship of the material, yielding consistent results. We validated different mix with different types of cements, different type of fibers. We saw that amorphous fibers lead to a lower deformation capacity, as a matter of fact, while still keeping the peak stress and peak strength. And so we employed this material in a full-scale project. This is the casting. I hope that the movie is showing. This is the casting that we made on the site. And this is a picture of the pilot structure that we were quite lucky to build by February 2020. You can see we have 3 compartments. The farthest one from our is ordinary reinforced concrete, and as you can see in the inlet on the top left, it's 10 centimeter thick. The middle one is cast in place UHPC, and so we were able to scale down to 6 centimeters thickness. So we have a saving of material of 40% actually. And then we employ the mixed precast and cast in place solution. So we precast horizontally the slabs that you see. They have holes so that when you cast columns, see the formworks there, the material flows through these holes and provides the connection to some kind of concrete dowel. In this case, the thickness of the slabs was just 3 centimeters. So there is a huge saving of material as compared to ordinary reinforced concrete, because actually you use 70% less. And this is a proof that the structure really can can take the function that it was designed for. These are based cooling the geothermal water which comes from the geothermal pits. It's full up to about 1.4 meter 8. And you can see that we had evidence of healing of some shrinkage cracks that formed. The other important thing for us, this water contains a lot of sulfates. So the problem is the degradation of the concrete itself. And you can see in the pictures on the left, you can see an image of ordinary reinforced concrete after 10 months about exposure to this water. The matrix is already corroding, whereas the rightmost figure is our UHPC material, ultra durability concrete as we call it, and it's practically intact, but for the change of color where the water was there. Yeah. Then let's make a step back.
3 minutes left.
Yes, the design. Well, obviously, when you start designing, you perform a linear finite element analysis. And for the 6 centimeter stick material, these are the stresses predicted. You are almost in the range of the tensile strength of material that you have. But when we go for 3 centimeter stick, actually, we found that in some cases, the elastic stress are higher than the tensile strength. Only these are structures which have a higher stress redistribution capacity, so we have to go for appropriate design methodology. So we use these are slabs, the yield line methods, and found that actually we have a safety factor. You can see here in the table on the top, we can withstand 8 of the water up to about 2 meters. So considering that the service level is 1.4 meter, we have surely extra safety for this. And we are now validating this concept with tests on slabs in the structure. The slabs are 1.5 meter by 1.5 meters. In this case, we are testing 60 by 60 centimeters, and you can see the crack pattern which is developing really according to the yield line methods we employed. You see the black dots on the white surface. We employed this for the digital edge correlation, and these are the results. These are really brand new tests, I would say, because we are still performing them in these weeks. And this is a picture from the top of our setup and a curve. Actually, this is not an elaboration. Tests were performed this week. So this is a picture of the morning in the lab, and you can see the remarkable, plastic behavior I will see of the slab up to a deflection limit of 10, 12 meters, which means about 1/3 of the thickness. So the issue is not exactly the ultimate limit state. We are confident about that. We have plenty of risks. The issue is the serviceability limit state, because these structures are much more deformable. So what we are doing now, we are working obviously to predict serviceability limit state, calculate the deflection. There is nothing new, principle of structural mechanics, the double integration of the curvature, but we want to implement into this model the degradation mechanism. So the removal of the thickness due to the attack of the sulfates. And as a matter of fact, if you have a cracked stage, as it can happen in the bottom parts of the slab, you will have a faster degradation because your diffusion coefficient will be higher. So this is the scheme of the methodology that we have implemented, was recently presented at the Rylem Week. So we start with first step of analysis. We calculate the crack width. We update the penetration rate of the aggressives. And so we progressively reduce the crack width as long as the penetration proceeds. And you can see, for example, the evolution of the displacements over time in the top right graph. You see after 50 years, you may have a displacement that you can no longer sustain, or even after 40 years. So this is the true end of service life in a sense, because your structure will become so deformed that it will become unserviceable. And this also implies aggressive reduction of the thickness that you can see in the bottom right graph. You start from constant thickness and you progressively reduce it as long as the fate attack it, but obviously you start attacking it more and reducing it more at the bottom. now are validating this. These are very last performing some tests in which we expose our specimens in the cracked state to aggressive environments while under load, set partial here, so to see whether the constitutive response of the material will change over time due to the contemporary action of sustained load and aggressive attacks. Most of this work is in our website, and we also in a MOOC that we have developed. We have published 14 papers that I've tried to collect here, so you can find everything there. They are on our website and they are all open access. And so I want to thank you. This was happy memories from our in-person meetings of the consortium of the project. And I also want to thank you consortium with the pictures of the pilots that we have produced. You can see the mussel raft in the Sea of Valencia, the offshore floater that we tested by going into it when we were in Valencia, the pontoon in Ireland, the graffiti of the water tower Malta, which was also tested in the last weeks, containing 400 cubic meters of water, as a matter of fact. So it was a huge test that we were really very keen and attentive to see how did it responded. And I really have to thank, because all this work could not have been done without the enthusiasm of all my students. I did not find any better way to thank them, putting here their pictures, and thank you, my research group at Polytechnic. Thank you very much for your attention.